Welcome to this deep dive. Today we're looking at support vector networks, or SVNs, really a pivotal algorithm for two-group classification problems.
Right. They came about mid-90s, and they really tackled some, let's say, weaknesses in the pattern recognition techniques that existed back then.
Like linear discriminants, early neural networks,
Yeah.
things like that.
Exactly. So our mission today really is to get under the hood, understand the core ideas, the innovations, what it means in practice, and importantly, how they actually performed.
And we'll be focusing pretty tightly on the research itself, the methods and results from the source paper. It's aimed definitely at a more technical audience, ML, data science folks.
Okay, so to really appreciate SVNs, we kind of have to look back a bit. The historical context is important. The paper itself mentions R.A. Fisher's work from way back in 1936.
Ah, right, on linear and quadratic decision functions. For normally distributed populations, I think.
That's the one. But Fisher already pointed out a challenge.
The parameters. Quadratic functions sound powerful, but you need to estimate a lot of parameters. Something like n plus 3n2 for n dimensions.
Precisely. And if you didn't have much data, trying to estimate all those could lead to pretty unreliable results. It was a significant hurdle.
Which is why linear discriminants were often preferred.
Yeah.
Right, much more parsimonious. Only n parameters in n dimensions.
Yeah, even Fisher often leaned towards linear methods for practical reasons. Fewer parameters, more stable estimates usually.
Okay, fast forward a bit. 1960s, we get Rosenblatt's perceptrons. Different approach altogether.
Networks of nodes, each node basically doing a linear separation. But the overall surface you got was piecewise linear.
And a key thing about those early ones, the learning, the weight adaptation, was mostly just in the final layer, wasn't it?
That's a critical point. You could transform the input non-linearly maybe, but the decision function itself was still linear in whatever space that transformation created.
Then the mid-80s brought a big leap. Backpropagation.
Right. Rumelhart, Hinton, Williams, also Parker, LeCun. Suddenly you could adapt all the weights in these multi-layer networks. That was huge.
Definitely opened up more complex models. But interestingly, the resulting decision functions were still, well, fundamentally piecewise, linear in character.
They were, which sets the stage for SVNs. The researchers behind SVNs were looking for something different, something geared towards really good generalization ability.
And their core idea was kind of counterintuitive. Mapped the input data non-linearly into a space with potentially many more dimensions.
You have very high dimensional feature space, yeah. And then construct a simple linear decision surface within that space. The magic was in the specific mapping and how that linear surface was defined.
Okay, let's unpack that, starting with the simpler case. Linearly separable data. Imagine you have two groups of points, and you can draw a straight line, or plane, or hyperplane perfectly between them.
Right, but there could be many such lines, right? Infinitely many, usually.
So which one do you choose? This is where the optimal hyperplane comes in.
Exactly. The key concept is the maximal margin. You don't just want any separating hyperplane. You want the one that's pushed as far away as possible from the closest points in each class. Maximize that gap. Figure 2 in the paper shows this visually.
And those closest points, the ones sitting right on the edge of this margin, those are the support vectors.
That's them. They literally support or define the position of this optimal hyperplane. They're the critical data points.
So mathematically, finding this hyperplane means solving an optimization problem.
Correct. You want to minimize the squared norm of the weight vector, WEAW, essentially making the hyperplane simpler in a way.
But subject to constraints. All the training points have to be correctly classified and lie outside or on the margin boundary. That's the YE, WA plus B, one constraint.
Precisely. Where Y is the class label +1 or mod of 1, EA is the input vector, W the weight vector, and B the bias.
And the solution, the optimal weight vector W0, has this really neat property. It can be written as a sum involving only the support vectors.
Yes. W0 equals the AI, I say I. And importantly, those coefficients, the A degrees, are only non-zero, actually strictly positive, for the support vectors themselves.
Meaning most of the training data doesn't directly influence the final boundary, only this subset.
Exactly, which is quite efficient. And finding those A-degree coefficients involves solving what's called the dual quadratic programming problem.
Okay, maximizing a function WAA subject to some constraints on the A's, non-negative, and summing to 0 when weighted by U.
Right, and there's a direct link between the maximum value of that function WAAO and the margin size WAO equals 1200. Maximizing W means maximizing the margin.
Fascinating. And the paper highlights a key theoretical result about generalization here.
Yes, a bound on the generalization error, the error you expect on new data, which depends on the ratio of the expected number of support vectors to the total number of training points.
And crucially, this bound doesn't explicitly depend on the dimensionality of the feature space.
That was a major insight. It suggests you could potentially map to incredibly high dimensions without necessarily suffering from the curse of dimensionality, if you could find a separating hyperplane with a relatively small number of support vectors.
That offers a path towards powerful classifiers that might still generalize well. A big shift from earlier thinking.
A very big shift. But of course, the real world isn't always so clean. Perfect separation is rare.
Right. Noise, overlapping classes, that's the norm. So the framework needed to handle non-separable data too.
Which leads to the idea of soft margin hyperplanes. They introduced slack variables, CLA5, one for each data point.
These slack variables, they allow some wiggle room. Like a point can be within the margin or even on the wrong side.
Exactly. The constraint y, W e psi plus b, of UR has to be non-negative. If UR is 0, the point is correctly classified and outside the margin. If it's between 0 and 1, it's inside the margin but still correct. If UR is greater than 1, it's misclassified.
So you allow errors, but you want to minimize them.
Precisely. The optimization objective changes. You still want to minimize W1 more, maximize the margin, roughly speaking, but now you also add a penalty term for the errors, which is C times the sum of all the error.
Minimize W1 war plus CP. And that C parameter seems important.
It's crucial. C is a regularization parameter. It controls the trade-off.
A trade-off between
Maximizing the margin, keeping W more, and minimizing the number of training errors, keeping phi small. A huge C means you penalize errors heavily, forcing the classifier to fit the training data more closely, potentially shrinking the margin.
Whereas a smaller C allows for a potentially wider margin, even if it means misclassifying a few more training points.
Yeah.
Which might actually lead to better generalization on unseen data.
Exactly. It lets you balance fitting the training set versus finding a potentially simpler, more robust boundary. Finding the right C is often done through cross-validation.
And solving this soft margin case also involves a dual quadratic programming problem, similar to before, but the constraints on the A coefficients change slightly.
Right, now they're bounded. Vol A, IA. This reflects the trade-off parameter.
Okay, so we have the margin concept, both hard and soft. But we talked earlier about mapping to high-dimensional spaces. Doing that explicitly sounds computationally expensive or even impossible if the space is infinite dimensional.
It would be. And this is where the famous kernel trick comes in. It was arguably one of the most elegant and powerful ideas in SVNs.
Instead of actually computing the coordinates in that high-dimensional space, you use a kernel function.
Yes, a kernel function, KU, is designed to directly compute the dot product between the mapped vectors without ever explicitly calculating E or B.
So you get the benefit of operating in that high-dimensional space, potentially finding linear separability where it didn't exist before, but you only need computations in the original lower-dimensional input space.
Precisely. It's a huge computational win. The paper mentions Mercer's theorem, which gives the mathematical conditions for a function Ku to be a valid kernel, meaning it actually corresponds to a dot product in some feature space.
And they give examples like the polynomial kernel, Ku equal v plus 1d. This lets you build polynomial classifiers of degree d.
Right. And they mention, for instance, a degree 2 polynomial in n dimensions can implicitly create a feature space with roughly NO2 dimensions. It grows fast.
And there are other types too, like radial basis function RBF kernels, which are also very widely used.
Yes, RBF kernels create decision boundaries based more on local similarity or distance. The point is, by swapping out the kernel function, KUV, you can create all sorts of different nonlinear decision boundaries using the same underlying SVN optimization machinery.
So the final decision function looks like fx equals sine, i.e. kix plus b, still a sum over the support vectors and I, but using the kernel function instead of a simple dot product.
Exactly. And practically speaking, building the SVN means solving that convex quadratic optimization problem. The paper notes that efficient algorithms exist, often working by iteratively focusing on the potential support vectors.
This flexibility through kernels makes SVNs quite universal, wouldn't you say? You choose the kernel to suit the kind of nonlinearity you expect in your data.
It absolutely contributes to their versatility. Now let's connect this back to generalization, which was the original motivation.
Okay. The paper talks about VC dimension. Babnik-Chervonenkis dimension.
Yes.
It's a measure of a model's capacity or complexity, right?
Roughly, yes. It quantifies how complex a set of functions, like the set of all possible hyperplanes, is. There's a theoretical bound on the probability of test error that involves this VC dimension, the number of training samples, and some confidence term.
And there's a tension. Lower VC dimension usually means better generalization bounds, but the model might be too simple to fit the training data well. Higher VC dimension lets you fit complex data, but you risk overfitting.
Exactly that trade-off. And the original optimal margin classifier for separable data fits nicely with Occam's razor principle here.
How so?
Well, it achieves zero training error, by definition of separability, and it minimizes WALO. Minimizing WI is related to minimizing the VC dimension for hyperplanes. So you're finding the simplest hyperplane in terms of margin that perfectly fits the data.
Maximizing the margin makes the boundary less sensitive to small changes in data points, intuitively leading to better generalization.
That's the idea. And the soft margin classifier with parameter C allows you to navigate this trade-off explicitly. By allowing some training errors, non-zero AVA, you might be able to find a solution with an even smaller RU or a better value for the overall generalization bound, potentially leading to better performance on unseen data, especially if the training data is noisy.
So it's a principled way to balance fitting the data you have with generalizing to data you haven't seen.
Precisely. And the paper didn't just present the theory, they backed it up with experiments.
Right, they started with some artificial 2D data sets using a second-degree polynomial kernel. Figure 5 showed those.
Yeah, illustrating how the SVN could find nonlinear boundaries and showing which points became support vectors and which, if any, in the non-separable setups, were errors.
And even with these complex boundaries, a key finding was that the number of support vectors was typically much smaller than the total training set size.
Yes, reinforcing that idea that the boundary is defined by a relatively small subset of the data. Very efficient representation.
Then they moved to a much harder real-world task: handwritten digit recognition. U.S. Postal Service database first. 16 by 16 pixel images.
And they used polynomial kernels again, trying degrees from 1 linear up to 7. They did some pre-processing, first centering, deslanting, smoothing, standard stuff to try and normalize the inputs a bit.
The results in Table 2 are really interesting. The error rate on the test set dropped quite dramatically as the polynomial degree increased from 1 up to about 6.
Yeah, the linear classifier degree 1 didn't do great, suggesting the data wasn't linearly separable, but the higher degrees significantly reduced errors.
And here's the fascinating part. While the error went down, the number of support vectors increased, but much more slowly than the dimensionality of the feature space, which explodes with higher polynomial degrees.
Exactly. This was strong evidence against severe overfitting, even though they were implicitly working in these massive feature spaces. It supported the theory linking generalization to the number of support vectors, not just the raw dimensionality.
They also compared it to other methods, like the Linet-1 neural network, which was state-of-the-art then. And the SVNs, especially degrees 2 and up, actually outperformed Linet-1 on this dataset.
And training times were reasonable, mostly depending on the number of support vectors found, not so much the polynomial degree itself. Very competitive.
But they scaled up again. NIST database. Larger images, 28 by 28, more data, this time using a 4th-degree polynomial kernel, and notably without specific pre-processing.
Right. They trained 10 binary classifiers, one for each digit versus the rest. Table 3 shows the results for each. Even with degree 4, there were still some training errors indicating the complexity or noise in the data.
But the overall performance on the test set, combining all 10 classifiers, was just 1.1% error.
Which was excellent. Figure 9 compares this to other benchmarks on NIST linear, KNN, Linet-1, Linet-4. The SVN result was highly competitive, sometimes state-of-the-art for methods without built-in geometric invariances.
And they make that point specifically. The SVN's performance didn't rely on knowing it was looking at images. You could randomly shuffle the pixels and it would perform the same, which isn't true for, say, convolutional networks. It was relying purely on the patterns learned via the kernel and margin maximization.
It really highlighted the power of the mathematical framework itself.
Okay, so let's wrap up. This deep dive covered support vector networks, a really novel approach back in the 90s. Key ideas: optimal margin hyperplanes,
The kernel trick for handling nonlinearity implicitly in high dimensions.
and soft margins for dealing with the messy reality of non-separable data.
And the experimental results, especially on digit recognition, were compelling. They showed strong performance, great generalization, often beating contemporary methods, even without encoding lots of domain knowledge.
It really demonstrated the power of the underlying principles.
Definitely. The work showed you could get impressive results on complex tasks, largely through these elegant mathematical ideas and letting the data speak through the optimization process.
Which leads to a final thought, perhaps. This work really makes you consider the balance, doesn't it? The balance between sophisticated mathematical models like SVNs, the quantity and quality of data available, and how much explicit domain knowledge we need to build into our machine learning systems. Where does the power truly lie, and how does that mix continue to evolve today?
That's a great question to ponder. SVNs were a landmark, showing what's possible with a strong theoretical foundation, and their influence is definitely still felt across machine learning research and practice.